Welcome back to the Foundry by Forge College. Last time, we looked at the historical context in those big, lofty design goals that paved the way for Bitcoin. But today, well, in this explainer, we're literally rolling up our sleeves. We're stepping away from the abstract theories of permissionless decentralization and getting our hands dirty with the actual physical gears of this decentralized engine. The title of today's explainer is Mechanics and Components of Nakamoto Consensus. We're going to lay it all out like a mechanical engineering blueprint to see exactly what makes this thing tick.
All right, here is our blueprint for today. We'll start with from goals to gears, then we'll check out the system components, watch the continuous loop in action, deal with some real-world friction and forks, lock it down with probabilistic finality, and finally, wrapping up the blueprint.
Okay, section 1, from goals to gears. So we spent our last session talking about these grand design goals, right? Creating a system that's permissionless, decentralized, and highly resilient to Byzantine faults. And honestly, those are beautiful concepts. But surviving malicious actors in the real world needs operational mechanics. Because concepts, they don't reach consensus on a global scale. Gears do. The mechanical reality here is a relentless, continuous cycle of proof of work and deterministic chain selection. These concrete repeating mechanics, they are exactly what bridge the gap between those high-level philosophical goals and a live, breathing, peer-to-peer network.
Moving on to section 2, the system components. Let's dive into this and lay our individual machine parts right out on the drafting table. First up, we've got the miner. They are our block assemblers, creating a new resource-intensive candidate history. Next is proof of work, which basically slaps a massive physical price tag on participation to secure the chain by pure cost. Then there's the gossip network. This peer-to-peer forwarding layer trades latency for true decentralization, which, inevitably causes some fun little propagation delays. Fourth, we have local validation. This is where every single node runs strict checks, so absolutely zero invalid data crashes the party. And finally, chain selection. The rule here is super simple. The chain with the most cumulative proof of work wins. This converges nodes without any voting, converting many independent proposals into one single agreed-upon ledger.
Section 3, the continuous loop.
All right, time to assemble those gears and actually turn the crank. And this brilliantly illustrates how the engine runs in an endless continuous loop. Step 1. A miner constructs a block candidate and iteratively computes proof of work until they find a valid nonce. Step 2. Once they succeed, they immediately broadcast that block out to the gossip network. Step 3. The neighboring nodes receive it and rigorously validate the headers and the transactions. And step 4. Those nodes apply the deterministic chain selection rule to decide, hey, am I going to adopt this new block or not? Over and over, block by block, this simple local math produces global agreement.
Next up, section 4, real-world friction and forks.
So what happens when our perfect theoretical machine crashes into the messy reality of global internet infrastructure? Well, it leads to a pretty fascinating, totally inevitable, and honestly mildly comedic scenario. What happens if two miners sitting on opposite sides of the planet yell bingo at the exact same time? Just picture it. Two miners in completely different rooms simultaneously finding a valid proof of work solution. They both hold up their winning block, kind of awkwardly looking around, fully expecting the grand prize. But because data takes actual time to travel, half the global network hears miner A first, and the other half hears miner B first. Just like that, we suddenly have a divergent network.
When this happens, we get what's called an orphan, or a stale block. This is a block that was completely mathematically valid, successfully broadcasted, but ultimately wasn't included in the final canonical chain. Why? Because the network never sleeps. It keeps churning. That chain selection rule acts as an objective, emotionless tiebreaker. Eventually, a new block gets mined on top of one of those branches, giving it more cumulative proof of work. The heavier branch wins outright. The loser, it becomes an orphan. And here's the harsh reality of that. That orphan block still burned a massive amount of real computing power and electricity, but its miner gets absolutely nothing. Ouch. Rough day at the office.
Let's see how this builds when the stakes are even higher, like during a full-blown network partition. Imagine a major internet routing failure temporarily splits the network straight down the middle. Because miners just keep doing their jobs, two long chains start forming entirely independently. When connectivity is finally restored, the protocol doesn't panic. It simply applies the chain selection rule. The chain with the most cumulative proof of work wins, period. The shorter chain is rolled back in an event called a reorganization or a reorg. So if you've ever seen a transaction suddenly unconfirm on your crypto wallet, this is exactly what just happened behind the scenes. And I really want to stress this. It's not a bug. It's just the decentralized machine resolving a split exactly as it was designed to do.
All right, Section 5, probabilistic finality.
This brings us to the underlying mathematical concept that resolves these temporary branches over time. Probabilistic finality is the reality that block reversals remain mathematically possible until enough cumulative future proof of work is layered on top, which makes a reorganization astronomically expensive. So the crucial point here is that finality in Nakamoto Consensus is never absolute the exact second a block is mined. Instead, it depends entirely on future mining work. Think of every subsequent block built on top of your transaction as an incredibly heavy security blanket, burying your data deeper and deeper into the immutable record. Which brings us to a magic number you've probably heard before, 6. You'll often hear that you should wait for 6 confirmations before considering a transaction truly settled. But why 6? Well, for Bitcoin-like parameters, this widely accepted heuristic reflects a very practical trade-off. It balances the time you're actually willing to wait against the exponential decay of reversal risk. Basically, by the time 6 blocks are stacked on top of yours, the sheer amount of hash power an attacker would need to rewrite that specific history is practically impossible to assemble.
Moving right along to Section 6, simulating the blueprint. To really cement this, let's move beyond the abstract and put some concrete numbers to our machine's mechanics using a minimal Python simulation. Imagine 3 mining pools. Pool A controls 40% of the network hash rate. Pool B has 35%, and Pool C has 25%. In our simulation, mining is modeled as a Poisson process, and message delays are modeled with random latency. What we observe is pretty cool. Pool A might find a block, but due to that simulated network delay, Pool B finds one too before it ever receives A's message. It proves that those inevitable forks we just discussed, they aren't just theoretical possibilities. They are the guaranteed mathematical result of relative hash rates interacting with random network latency. And if we intentionally crank up the network latency or shorten the block intervals in our simulation, well, the machine gets pretty chaotic. The direct consequence of doing that is a drastically increased fork rate and much lower confirmation confidence. Adjusting these variables directly dictates how often our simulated nodes disagree on the chain head. It's an incredibly delicate engineering balance.
And finally, Section 7, wrapping up the blueprint.
We have covered a lot of ground today, looking at the functional blueprints and literal code mechanics of this remarkable system. So I want to leave you with this one defining thought. Temporary forks, stale blocks, and short reorgs are not signs of a protocol bug. They are natural outcomes of how propagation and independent mining interact. Nakamoto Consensus is not a rigid, perfectly synchronous piece of software. It is a highly resilient, dynamic, self-correcting machine that leverages physical cost and simple local rules to achieve robust global agreement. But understanding this operational blueprint leaves us with one massive provocative question. We know how the machine handles natural network friction, but how will these mechanical gears hold up against a coordinated, malicious attacker who actively wants to rewrite history? What happens when someone intentionally tries to exploit these probabilistic mechanics? Well, we're going to tear into exactly that in our next explainer. Until then, to explore more Web3 fundamentals and continue your educational journey, be sure to visit forge.college. Thanks so much for joining me today on The Foundry, and I will see you in the next one.